Bonjour à tous. Bonjour à tous. Nous allons poursuivre notre session, très intéressante session de conférence, avec M. Gary Pierce et Mme Lauricia Baino. M. Pierce est géologue depuis plus de 40 ans, principalement comme consultant dans le domaine des métaux rares et des minéraux industriels. Tout au long de sa carrière, il a publié plusieurs articles techniques et a été impliqué dans la préparation et la rédaction de plusieurs études économiques préliminaires, de préfaisabilité et de faisabilité définitive. De plus, il a agi en tant que consultant ou gestionnaire sur les projets importants de pegmatite à spodumène. Mme Baino étudie présentement en vue de l'obtention d'une maîtrise en géologie économique de l'Université de Western Ontario. Sous la tutelle du Dr. Robert Linden, elle étudie la relation entre la déformation et l'emplacement de la pegmatite de lithium du gisement Whabouchi au Québec. Elle agit également à titre de présidente du chapitre étudiant du Society of Economic Geologists de London. Il nous présente présentement la propriété Whabouchi, ressources mondiales et métallurgie innovatrice. Madame Bain.
Thank you. Good morning. I'll be presenting to you specifically the geology of the Whabouchi project. But first I'll start with an overview of pegmatites and their classification and where the Whabouchi pegmatite falls. So based on the classification scheme of Cherney and Ursit, revised in 2005, we have 5 different classes of pegmatites. Starting with the one at the deepest depth, we have the abyssal, followed by the muscovite, with getting shallower as we go along. Then we have the muscovite rare element, the rare element class, and then finally the marlitic. Pegmatites account for about 30% of the world's lithium resources, and most of these lithium minerals are found in the complex type within the rare element class. And they have served as the most economic significant source of lithium in pegmatite, such as the green bushes in Australia. However, we have the Whabouchi pegmatite, which falls under the same class, but is known as an albite spodumene pegmatite, and it's showing itself as one of another significant, as more economic than previously known. The Whabouchi pegmatite is one of the largest albite spodumene pegmatites in the world, with measured and indicated resources of about 25 million tons of 1.54% lithium oxide. And the spodumene tends to occur in this pegmatite as green spodumene, shown here in this photo. The Whabouchi dike is approximately 1.3 kilometers in length along strike, and it's striking towards the northeast at about 60 degrees. At its widest, it's 130 meters wide, and it goes to a depth of about 300 meters. The Whabouchi project is located 280 kilometers northwest of the town of Chibougamau, with excellent access along the route du Nord. It is also located about 30 kilometers east of the Creek community of Nemaska. Geologically, the pegmatite intruded the Lac de Montagne volcano-sedimentary belt of the Opinaka subprovince, and shown by the star right here. Oops, sorry. Shown by the star here, and it's boundaried by the Champion Lake granitoid to the north and the Opatika subprovince to the south. This is a preliminary map of the property. We have several different rock types. Shown here, the red indicates the different pegmatites found outside of the albite spodumene pegmatite, shown in bright green. We also have metabasites, shown by dark green, ultramafics, shown by purple, and basic granites, shown by pink. So the first of the rock types is pegmatite, and there's several different pegmatites on the property. The first being the simple biotite garnet pegmatite, which is found mainly in the northern part of the property. It tends to occur with biotite exceeding 10 centimeters in length. In this sample, they're about 5 centimeters in length. And the garnets are occurring in trace as dark, small garnets, less than a millimeter in size. As we move southward or more proximal to the Whabouchi pegmatite, the actual spodumene pegmatite, we run into the muscovite biotite garnet type pegmatite. Here we typically have a higher percentage of muscovite within these pegmatites, and they can exceed 10 centimeters in length as shown in the photo. And as we get even closer to the albite spodumene, we find ourselves with the muscovite garnet type. Garnets can be upwards of a centimeter in diameter, but for the most part, they occur as aggregates of about a millimeter in diameter. And finally, but most importantly, we have the albite spodumene pegmatite, where spodumene accounts for about 30% of the overall mineralogy of the pegmatite. And these spodumene crystals shown here in, as I said before, most of them are green. Some of them actually are a bit whiter than this, but they range in size from a couple millimeters to up to 50 centimeters in size. Outside of the area of the Whabouchi pegmatite, we run into granites. Most of them have the texture shown here, and within them we have pegmatitic veins or pegmatitic sweats occurring within them, hence their name, the pegmatitic granites. And for the most part, these granites show no deformation whatsoever. Of the last two rock types, the orthonites and the metabasites, which I'll show you as I go along, these record most of the deformation in the area, and in this example of the orthonites, we have well-defined lineations and foliations, and most of the lineations across the property actually look just like this. They're all subvertical. And lastly, we have the metabasites. This is an example of metabasites found at least a kilometer away from the albite spodumene pegmatite, and then as we get closer, the metabasites show polydeformation, just like in this photo here. As I said before, we have subvertical lineation shown in the orthonices, but in the metabasites as well, we can see clearly the subvertical transmission foliation that has developed. And these tend to show some dextral sense of shear. That is more pronounced here in the photo, showing the boudinage pegmatitic dike in one direction and the shortening of a very small pegmatitic vein in this direction. We also have other features, deformation features of the pegmatite, where we have the filling in of brittle fractures by subsequent albite spodumene pegmatitic material. And lastly, as a summary of the deformation of the area, we see that the pegmatite is hosted in a subvertical high strain shear zone, which is a transpressional zone, and it has a strike of about 60 degrees. The lineations measured are shown here by the red triangles, and the foliations, the poles of foliations used, are shown by the black circles. So the rocks in the shear zone are thoroughly transposed with steeply dipping foliations and well-developed lineations. And now I will pass you on to Mr. Pierce.
I hope I can work all this. Let's just change the slides here.
This one is for the slide.
Oh, I see. Okay.
This one is the laser.
Well, that's just a pointer. Yeah?
Pointer.
Okay. All right. Thank you. Well, good morning, everyone. I'm very, very pleased to present on the Whabouchi hydrometallurgical processing. This very innovative process is perhaps the first change in the technology in about 65 years or so. The latest boom in lithium markets and so on, attracted a bunch of people into the lithium industry for the first time in many, many years. And most of them brought along with them the old technology of processing and so on that had been well established. And even in Asia and an effort in by Taliesin some years ago was really to replicate the old U.S. Bureau of Mines technology. In this case, we looked at the assets that are specifically here in Quebec, and the major one is, of course, electricity. And so we looked at all the potential ways of maybe optimizing the use of Quebec resources, and we also had a green outlook. We wanted to be sure that what we were doing was we're producing materials for a green industry, so we wanted to be sure we were also operating as green a fashion as we could. So we'll start you with this is a quick overview, and the first part of the process here is pretty much standard. We have a concentrate that runs about 6% lithium oxide. We roast this and acid bake it with sulfuric acid, and then we leach it with water. And then the job is to purify the solution, which is a lithium sulfate solution, to get it ready for the final production of products. Is this the? Oh, there we go. This is just a flow diagram of the process, and the first part is pretty much standard in that it's the leaching and recovery of the lithium from the acid bait concentrate. And there we end up with a product that contains, we've removed iron and aluminum pretty much completely, but we've have to move it on to a secondary impurity removal where we raise the pH with in our case, lithium hydroxide, which we can then recover again. We use some of our product to raise the pH of the solution for a secondary purification, and then that goes back into the stream and is recovered again. We reduce everything down. We get rid of the iron, aluminum, silicon, and manganese, and so on. And the last two things are calcium and magnesium, which we have to move down to below 5 parts per million in the solution to be able to make the products themselves. And we found we can remove it right down to 1 part per million, or just depending on how much of the ion exchange process we want to employ to do that. And once we have put it through that process, we then go to the IX, ion exchange process, in which we pass the material through and end up with a very pure lithium sulfate solution. And this is where the innovative part of the process occurs. And we'll go through that through a little more attractive diagrams here. This looks almost like some kind of rocket science here. This is the primary leach and the leach rather, and the primary purification cascades down through these tanks here. And this is, we have manganese has been removed in the secondary process. The last bit of manganese is removed, and the magnesium and calcium considerably reduced down to below 200 parts per million in the lithium sulfate solution. Here's the IX columns, ion exchange. These units, you pass the solution through a resin in the IX solutions, and this selectively takes out calcium and magnesium. And through, depending on what we call the number of bed volumes, we've done the experimentation to know how many bed volumes are necessary to remove it down to below the 5 parts per million. And now we come to, this is a schematic diagram of the membrane electrolysis or electrodialysis. It's essentially, it's a similar kind of thing that you might hear of for somebody having kidney dialysis. It's a way of splitting the salts and so on, and so on. So we introduce the lithium sulfate into the central compartment, and with electric power, the lithium ion is attracted to the cathode, where it will react with the water that's been broken down to hydroxide here to make lithium hydroxide in this cell. The sulfate goes across the anodic membrane into the analyte compartment, where it combines with the H2 to make sulfuric acid. And these are continuous, this is a continuous flow, and you'll see this is a little more complicated diagram, but you're continually adding new lithium sulfate to the central compartment, and you're maintaining the exact tenor of lithium hydroxide in the cathodic compartment and the sulfuric acid in the anodic compartment. They're flowing out while new material is flowing in, so you're maintaining a concentration of the material that will ultimately go to, in the case of lithium hydroxide, will go for crystallization into lithium hydroxide monohydrate. So it looks very complicated because you have to add new material, you have to remove the lithium hydroxide, but introduce a lean solution to take on more lithium hydroxide, and the same thing with the sulfuric acid, and also, of course, you're introducing new lithium sulfate into the central compartment. And this is how it looks in laboratory. This is a set. The three compartments can be replicated, so you end up with a battery of these, and they're very narrow spaced. And in the actual technology itself, each compartment is only about 2 millimeters wide, because the efficiency of the process in its use of electricity depends on how short a distance these ions have to move. And so you don't want to use up a whole lot of electricity heating up the solution with these ions having to make a long journey through. So it's quite a remarkable thing to see so much solution come through compartments that are only 2 millimeters in diameter. Now, this is another innovative part of the processing, in that we can make what's called 4-9s lithium carbonate directly with no middling product and essentially very little waste. It's a 93.7% recovery of lithium carbonate, and using lithium hydroxide, very pure lithium hydroxide product. We can put some through there and so on. The beauty of the situation with this one is you have the first one. I'm sorry, I should back up there. This is the lithium hydroxide carbonization circuit, and this in here is the main place where we make lithium carbonate from lithium hydroxide. So we're making two products here, the lithium carbonate and lithium hydroxide. And this, but when you make this, you end up with a solution. You make a lithium carbonate precipitate plus a lithium bicarbonate solution that needs to be heated to drive off carbon dioxide, and then it will precipitate another final amount of lithium carbonate. And overall, the efficiency of that process is 97.3% efficient in recovering lithium carbonate. These are this is the the laboratory lithium conversion reactor, lithium hydroxide, and this is they call it decomposition precipitation circuit because you have lithium bicarbonate in solution. You heat it up, drive off the carbon dioxide that it took with it, and it'll then precipitate again. As this is a demonstration plant that will be up and running in 2013. We'll be producing 400 tons a year of lithium hydroxide and about 65 tons of lithium carbonate. The beauty of the combination is when you make the lithium hydroxide monohydrate, the efficiency of that crystallization is only 75% recovery, and you end up with a purged solution rich in sodium hydroxide that also follows the lithium all the way through. And this is ordinarily a waste product. We use it to feed back for altering the pH in the solution and then recapture the lithium units as they go through. And we also can send the purge solution directly to the lithium carbonate precipitation circuit and produce lithium carbonate from this otherwise waste solution. This is the main competitive and environmental advantages of the Nemaska process. For one thing, our reagents are Quebec electricity and carbon dioxide that we would take from the atmosphere. And so we have a pretty good handle on prices going forward. They're stable and so on. Whereas the competing methods use 35,000, 40,000 tons of sodium carbonate, which is a product that's shipped by rail, most likely from western United States, and the pure lithium hydroxide is made in the standard method using very pure sodium hydroxide as the reagent to react. And of course, those prices can vary, and it's hard to sign a long-term contract with a person who's going to take your product. If you have an idea what your costs are going to be for the next 3 or 4 years, you can make a deal with your customer for longer-term supply agreements. And this is one thing we have heard a lot from people who buy this material is they're anxious to know what their product is going to cost, especially going into manufacturing electric automobiles and so on. The nice thing about the clean and renewable reagents, we don't introduce any impurities into the product, and we don't introduce any impurities into the environment. And the lithium recoveries are considerably higher using the Nemaska process. For the one thing, we can take that waste solution from the lithium hydroxide monohydrate crystallization, which is 25% of the material, and we can put it then through our lithium carbonate circuit, and it's essentially free feed. Otherwise, it's a waste product that is a bit of a nuisance to get rid of. And we're able to convert 97.3% of that waste into very high purity lithium carbonate. And this gives us much higher recoveries. And the flexibility of the technology is such that we can reduce the lithium hydroxide monohydrate production and direct more lithium hydroxide to the lithium carbonate circuit, and we can balance the thing to fit the market for the two major products in the market. Thank you.
Thank you, Mr. Pierce, and thank you, Ms. Barno. We have time for one question, quick. Temps pour une question. Monsieur?
I can hear you, I think.
Did you obtain some patent on parts of your process?
Yes, there are several parts of the process, and there's some new stuff that we haven't put out yet that comes in and near the front end of the process as well, and they are patented by Nemaska.
Thank you.
Thank you.